This presentation accompanies the paper Generating Utilization Vectors for the Systematic Evaluation of Schedulability Tests, published at RTSS 2020. The research was done by David Griffin, Ian Bate, and myself, Robert Davis, all of whom work in the Real-Time Systems Research Group at the University of York. The focus of this research is on the Dirichlet-Rescale, or DRS, algorithm. This algorithm has a relatively simple signature. It returns a vector of n components, or utilization values, such that the sum of those component values adds up to the total utilization required. And also, the individual component values are upper and lower bounded by individual maximum and minimum constraints. Thus, the inputs to the algorithm are n, the size of the vector required, u, the total utilization required, and optionally, two vectors specifying maximum and minimum constraints. The motivation for this work comes from the need to support systematic evaluation of the effectiveness of schedulability tests. To do that, it's necessary to generate the synthetic task sets with a variety of different parameters that are used. And in order to do that, it's necessary to generate unbiased vectors of utilization values that are compliant with some constraints. And it's this foundational layer that's the focus of this work. There are three key criteria for the generation of utilization vectors. These are uniformity, efficiency, and flexibility. In terms of uniformity, the vectors of utilization values generated must be unbiased. In other words, the vectors must be uniformly distributed within the valid region. Bias in the sets of vectors generated can undermine the conclusions drawn from studies into schedulability test effectiveness. Efficiency is also important because it's necessary to generate millions of task sets to achieve statistically significant sample sizes when conducting wide-ranging systematic evaluations of schedulability test performance. The algorithms also need to be flexible. By that we mean capable of handling constraints on individual task utilization values. This is needed so that the utilization vectors can be tailored to the specific requirements of the problem at hand, and I'll give some examples of that later, while still producing a uniform distribution of vectors within the valid region that's given by the set of constraints. I'm now going to give you some mathematical background needed to understand the operation of the DRS algorithm. So we're interested in n-dimensional vectors with component values that sum to a given value, u. Now, here each vector can be considered as representing a point in n-dimensional space. And to ease visualization here, we're going to draw diagrams for the case of n equals 3, so 3D space. Now, the canonical form of the problem is that the sum of the component values is equal to 1. So in the 3D case, that's like the three coordinates, x, y, and z, sum to 1. And as these are utilization values, we also have the constraints that x, y, and z are greater than or equal to 0. Now the equation x plus y plus z equals 1 defines a hyperplane in general, but here just a plane in 3D space. And when we combine that canonical equation with the inequalities, then that defines a standard n-1 dimensional simplex, which is embedded in n-dimensional space. So in the simpler case, that's just a triangle in 3D space, as shown in the diagram. And the vectors that we require are points that are uniformly distributed within this simplex. Now, if we add constraints, then the maximum constraints form a constraint simplex, which is on the same hyperplane as the standard simplex. So here in the diagram, we have the additional constraints that x is less than or equal to 0.5, y is less than or equal to 0.45, and z is less than or equal to 0.7. Now the vectors that we require are points that are uniformly distributed within the valid region, in other words, within the intersection of the constraints simplex and the standard simplex. Now, we note here that there's an interesting duality between the two simplices. We could generate points in either simplex and use the other one as the constraints. And actually, in the DRS algorithm, we make use of this duality to improve efficiency. Minimum constraints can be handled by transforming the problem into a canonical form where all the minimum constraints are zero. So we're going to ignore minimum constraints for the rest of this presentation. However, you can see how they're handled in the paper. There has been some related work done in this area. In fact, the first work on this topic published in the real-time systems literature was on the U-Unifast algorithm. This solves the problem with no maximum or minimum constraints, and so is useful for single processor systems. In the mathematics literature, Olkin and Rubin published work on the Dirichlet distribution, and this can also be used to solve the problem with no constraints for single processor systems. For multiprocessor systems, maximum constraints are required since the total utilization required may be more than one, but having individual task utilizations of greater than one is invalid. So for this purpose, the U-Unifast discard algorithm was developed. And this addresses the problem of both maximum and minimum constraints. It uses a very simple, naive approach. Points are first generated using U-Unifast, and then any points which do not comply with the constraints are simply discarded. Unfortunately, U-Unifast discard suffers from what's referred to as the curse of dimensionality. For example, if the constraints on each component halve the volume of the valid region, then the proportion of useful points to the total generated is 1 over 2 to the power n, which is perfectly fine when n equals 3, but not so good for, say, n equals 50. The round-fixed sum algorithm, invented by Roger Stafford and adapted for task set generation by Paul Emberson, efficiently addresses the problem when you have symmetric maximum and minimum constraints. That's where the constraints are the same for all tasks. And it has become the de facto standard approach for modelling task utilization values in multiprocessor systems. Unfortunately, round-fixed sum does not cater for asymmetric constraints, and it can't be adapted to do so because of how it relies on symmetry for its efficiency. The DRS algorithm was designed to cope with asymmetric constraints and to address the intractability drawbacks of U-Unifast discard, which discards points, and those of round-fixed sum, which would need to generate points in very many different simplices to deal with a valid region that is in irregular shape. The basic concept of DRS is to generate a point on the standard simplex, and if it is not in the valid region, to make a series of transformations, shifting the coordinates of the point until it is within the valid region. And crucially, these transformations must preserve the uniform distribution of points. So let's see in outline how the DRS algorithm works. First of all, it transforms the problem into a canonical form where the required utilization is 1 and all of the minimum constraints are 0. It exploits duality to switch between the standard and constraint simplices for efficiency. It then generates a point P on the standard simplex using the Dirichlet distribution. If point P satisfies the constraints, then it's returned, reversing any initial transformations that were made. Otherwise, the algorithm defines a simplex S based on all of the constraints that are broken. This new simplex S, by definition, contains the point P. Simplex S is then mapped onto the standard simplex via a matrix transformation. This scale and translate transformation alters the coordinates of point P, making it more likely that the point will now be in the valid region. The algorithm then goes back to step 4 and checks if the new coordinates of the point meet the constraints, in which case it's finished, otherwise it iterates with further scale and translate transformations. So let's see how this works. Looking at the simplex S that contains point P on the diagram, we can now see how it's mapped onto the standard simplex. So in this case, point P has moved closer to the valid region, but is still not within it. And so again, we need to construct a simplex S based on the broken constraints, which is actually just the same as it was before. And then once again, we make a rescale operation which maps simplex S onto the standard simplex. And here we can see that now the point P has moved to within the valid region. So the algorithm has now converged and will return this point. The key aspect of the way in which the DRS algorithm operates is to ensure uniformity. So the distribution of initial points that are generated over the standard simplex is uniform, and hence the distribution of points is also uniform over the simplex S. As the matrix transformation that maps simplex S onto the standard simplex is an affine transformation, in other words, it just does scale and translate operations, the points that are uniformly distributed over simplex S become uniformly distributed over the standard simplex, and hence they're uniformly distributed over the valid region. So that's how the algorithm works. The final thing is to ensure that it converges, that these transformations cannot continue forever. And this is shown in the paper. As an illustration of convergence, we can look at a heat map of the initial points. So the diagram on this slide colour codes how many rescale operations are required before the 1,000 different initial points move to within the valid region. And here the valid region is the inverted triangle shown in blue in the centre. So points that are initially in the valid region require 0 rescales. Those colour-coded in turquoise require 1, in green require 2, in yellow 3, orange 4, and red 5. In the worst case here, a maximum of 24 rescale operations were required. However, this was done for illustration purposes with the duality optimization disabled. If we didn't do that, then no rescaling would be necessary, since every point would be generated within the smaller constraints simplex. We conducted a number of experiments that investigated the performance of the DRS algorithm. In experiment A, we looked at task sets of cardinality 50 and did 10,000 runs for each utilization value from 0.05 to 0.95. For each run, we called the DRS algorithm with a set of randomly generated maximum constraints produced by UUnifast. In the diagram, which shows a box plot of the number of rescale operations required, you can see that the worst case occurs for a required utilization of 0.5. And this happens when the constraints and standard simplex are of the same size, and we can get no benefit from the duality optimizations. Notice that the maximum number of rescales, even the outliers, is less than 200 in each case. Our second experiment was very similar to experiment A, but we fixed the required utilization at 0.5. Recall that that was the worst case. And then instead we varied the size of the vectors n from 5 to 100. Again, we did 10,000 runs, this time for each value of n. Notice that in the diagram, the number of rescales gradually increases with increasing size of the vectors. However, again, the maximum number of rescales required is bounded by 200. This slide shows further information from experiment B. When we have a large number of rescale operations, particularly for large vectors, then this can lead to the accumulation of floating point error. In this case, we do what's called a retry. So a retry effectively discards the initial point and tries again with another one. A retry is done by generating another point if the total error, that's the sum of the component values minus the actual required utilization, exceeds 1/100th of 1%. We can see from the graph that the number of retries increases with increasing size of the vectors, but it remains below 3 for n less than or equal to 100. In the third experiment, we examined the runtime required to generate all of the vectors needed for a sort of standard benchmark schedulability analysis experiment. So here we generated 18,000 vectors at a variety of different utilization levels. We used a Pi4 to obtain reliable timings, and we found that the runtimes, as shown in the graph, are well approximated by a polynomial of order 3, in other words, a cubic function. Now, normally we would not run the DRS algorithm on a Pi4. Typical use would be to run it on a laptop or desktop PC, or even possibly on a server. So we also took some timings using an average laptop machine and found that it takes around 6 seconds to generate all 18,000 vectors for a benchmark schedulability analysis experiment using 10 tasks in each task set, and around 6 minutes for all 18,000 vectors if we have 100 tasks in each task set. In the fourth experiment, we verified the uniformity of the distribution of vectors produced by DRS by comparison with U-unifast discard. So what we did here was to examine the density of points produced within 1,000 small reference simplices within the valid region by DRS and by U-unifast discard. We compared the empirical cumulative distribution functions using the KS test. This gave a KS statistic of 0.04 and the largest possible p-value of 1.0. This means that there's absolutely no evidence that the vectors produced come from different distributions, and so statistically speaking, we cannot reject the null hypothesis that the distributions are the same. The main use of the DRS algorithm is in the systematic evaluation of schedulability tests. Here it's used to underpin the generation of synthetic task sets with their execution times derived from the utilization values that the algorithm produces. The DRS algorithm supports asymmetric constraints. These occur when execution times have multiple values or they're composed from multiple constituent parts. Examples include mixed criticality systems with C-low and C-high execution time budgets for each task, where the former value is always upper bounded by the latter. They occur in multi-core systems where the overall execution time of a task is made up of processor demand, bus demand, memory demand, and so on. DRS is also useful for systems where we're interested in typical and worst case execution times, and in systems that have both execution times and self-suspensions for tasks, or execution times and resource locking times. DRS can also be used for systems where there's no constraints or systematic constraints. Hence, it can be used as a replacement for U-unifast for single processor systems, and also for RAM-fixed sum and U-unifast discard for multiprocessor systems. Taking mixed criticality systems as an example, we reproduced one of the schedulability analysis experiments from the original paper on adaptive mixed criticality from 2011. Only here we used the DRS algorithm as the basis for task set generation, and this allowed us independent control of the total low criticality utilization and the total high criticality utilization. It also allowed us to make independent selection of the low criticality utilization and high criticality utilization for each task, subject to the appropriate constraint. By doing so, we were able to eliminate the generation of all infeasible task sets. This slide shows the results of two versions of the same experiment. The graph on the left is reproduced exactly from the original AMC paper, while that on the right is just the same experiment but using the DRS algorithm in task set generation. Here it's important to note that by using DRS, we were able to generate valid task sets with low criticality utilizations all the way up to 1. By using the improved methods of task set generation that DRS supports, we can see a much sharper transition in schedulability for the AMC method than for SMC, and also a much larger improvement by using AMC over SMC. So by using DRS, we're able to get more nuanced and realistic results, and these could affect the decisions on which methods to use in practice. Why is it important to use an unbiased distribution of utilization vectors? Well, what do we mean by unbiased? Well, the distribution is unbiased if the vectors generated are uniformly distributed across the valid region. This does not mean that the component values themselves are uniformly distributed. That's a common misconception. So why use an unbiased distribution? Well, for schedulability analysis experiments, using a uniform distribution of utilization vectors means that each possible vector that complies with the constraints has the same chance of being selected. The distribution is thus unbiased. It provides full and fair coverage of all valid possibilities, and it's therefore arguably the appropriate one to use. Not using a uniform distribution of vectors risks biasing the results of the schedulability analysis experiments. Unfortunately, there are a number of simple ways of generating task utilization vectors that introduce bias. The first is to select individual task utilization values from a uniform distribution between 0 and 1, and simply keep adding tasks until the required total utilization is reached. Unfortunately, this confounds task set cardinality and task set total utilization, so we cannot distinguish the effects of one from the other when performing schedulability analysis experiments. Another method called U-scale selects n values of individual task utilizations from a uniform distribution and then scales them to achieve the required total utilization. The figure at the top of the slide shows that this results in a distribution of task utilization vectors which is not uniform across the valid region. This also happens and is shown in the diagram at the bottom of the slide for a method called UAdd. Here, UUnifast is used for each of multiple component parts of individual task utilizations, and then these partial values are added together. In conclusion, why as researchers should we be using the DRS algorithm? Well, this is a flexible general purpose algorithm that supports asymmetric constraints on both the maximum and minimum utilization of individual tasks. It can be used to obtain unbiased distributions when execution times have multiple values, for example in the mixed criticality case, or are composed from multiple parts, for example in the multicore case. DRS is useful for tailoring task sets to specific problem requirements, limitations, or domain-specific constraints. It can also be used to replace UUnifast, UUnifast discard, and rand fixed sum. The DRS algorithm has high performance. It supports efficient generation of task sets with cardinality up to 100 with individual constraints. And our additional experiments have shown that it can support task set generation up to cardinality of 200 with a commensurate slowdown in performance. The Python source code for DRS is publicly available and permanently archived. It can be installed via the simple process of pip install DRS. And we've also provided a C library enabling the DRS algorithm in Python to be called directly from C or C++ code, implementing schedulability analysis frameworks. That brings me to the end of this presentation. I hope that you've enjoyed hearing about the DRS algorithm and will go on and read the paper to find out more details about it, and also use the DRS algorithm in your own research. If you'd like to find out more about it or you have any questions, then you can get in contact with me, Rob Davis, at the University of York. There will also be an opportunity to ask questions at the live session as part of RTSS 2020.